All right, so we're going to finish up 11.1 by looking at a formula to add up numbers for us. This formula only works for a certain type of sequence. Let me show you an example. Let's say you have these numbers. So this is 11.2 part 1. This is, yeah, we're still doing, this is 11.2, but we're still finishing up something yesterday. And let's say that that just kept going. So what's the pattern there? I'm adding 2 each time. What's happening to the numbers as they continue? Let's say they continued forever. What are they approaching? They're approaching infinity. You can't add all the numbers from 2 in this pattern up forever because they're just getting bigger and bigger and bigger. So if you want to add up a lot of numbers in a sequence, they can't be getting bigger forever. Otherwise, when you add them up, the answer just approaches infinity. So let's look at something like this. Let's do 4, 2, 1/2, 1/4, 1/8, 1/16, 1/37. What's the pattern in this one? Yeah?
It's reduced by half.
Right. Each time, the number is getting half as big as it was before. So if this continued forever, eventually the numbers that I'm adding are getting closer and closer to what if I were to add all these up? It's getting closer and closer to 0. This is an example of something we can add up the numbers for because they're getting smaller and smaller each time. And eventually they get so small they don't even really make a difference anymore. Let's add up a few different examples. Let's do some partial sums. And then I'm going to show you how you can do this without doing it by hand. If you add up the first 1 numbers in that pattern, what do you get? Yeah, 4. What if you add up the first 2 numbers? 6. The first 3? 6.5. And how about the first 4? 6 3/4. If you were to add up every number forever, this would add up to 7. And you can probably see the sum is starting to get closer and closer to the number 7. Now, I'm going to show you a way we can add these up without having to do it by hand. Does anybody remember what kind of pattern this is called when you multiply by a number to get from one to the next?
Geometry.
That's geometric. Yep. And there is a formula to add up a finite amount of terms. So we're not talking about infinite. We're just talking about maybe the first 5, the first 20. You can do the first 1,000,000 if you want. But you're stopping somewhere. This is the formula for adding up terms in a geometric sequence. You need to know 3 things. What's the first term in the sequence you're adding up? What are you multiplying by each time to get from one term to the next? And how many terms do you want to add up? You want to add up the first 2, first 3, first 4, first 5? How many do you want to do? So we're going to try that formula on this problem. Let's try to use this formula to add up the first 2 terms for us. Now we can add up the first 2 terms in our head very quick at 6. But if I said to add up the first 50, we could do it just as fast with this formula as you could with the first 2. It doesn't make a difference how many you want to add up if you use a formula. Okay, so what's the first term? So 4 times And what are we multiplying by each time to get from 1 to the next? 1/2. And how many are we adding up this time? That's my exponent. 2. So we're going to raise that to the second power. And then the bottom is 1 minus 1/2. This should come out to 6. Let's see. All right. I'm going to do what's in parentheses first, and then I'll multiply by 4 at the end. All right, so 1 minus 1/2 squared. Okay, there's the top, 0.75. Divided by, the bottom is 1 minus 1/2. Yeah, it's just 1/2, but we can type it in. Okay, so that's the bottom. And now I still have to multiply that by 4. I got 6. Which is exactly what we got, adding up the numbers by hand. Let's try it for S sub 4. Let's see if we add up the first 4 terms with this formula, if it gives us 6.75. It should. All right, so first term again is what? 4 over, and everything here is going to stay the same, except this exponent is going to become a what? Because we're going to add up the first 4. So it's it's going to be a 4. Everything else stays the same. And that's the formula to add up the first 4 terms and see if we get 6.75. Okay, so 1 minus 1/2 raised to the 4th. So that gives me a numerator of 0.9375. Divided by, let's just do this in our head. What's 1 minus 1/2? 1/2. So divide by 0.5. And then multiply everything by 4. I'm not too smart. What's half of 2? 1. So that messed up our S4 a little bit. I forgot to take half of 2. So let's add these up. What's 4 plus 2 plus 1 plus 1/2? That should have added up to 7.5. That didn't mess up the first one we did because I didn't go that far in the first one. But half of 4 is 2, half of 2 is 1, half of 1 is 1/2. Everything else is okay. 4 plus 2 plus 1 is 7, plus 1/2 is 7.5. And that's exactly what we got when we use the formula. That's why you want to use the formula, because it's too easy to make a mistake like I did doing it by hand. It's very easy to mess something up. Any questions on that? All right, let's try one more. This time I want you to add up the first 12 in that sequence. But you don't have to find them. All you have to do is figure out the first term and what you multiply by each time to get from one to the next. Okay, so n, that's the easy one. That's how many you're adding up. We're adding up 12. A1, that also is pretty easy. That's the first term, which is always given. This time it's 2. And R is the only one you have to figure out. What do you multiply by each time to get from one to the next here? 1/3. Yep. Now that you have those 3 pieces of information, you can fill them into this formula, and it will add up the first 12 numbers in that pattern. Without even knowing what all 12 of them are. You don't need to know. You can just add them up without knowing. Okay, so S sub 12. All set? Perfect. First term times 1 minus r to the n So 1 minus, what's r? 1/3. And what power are we going to raise the 1/3 to? 12. All divided by 1 minus r. We can simplify it if we want. What's 1 minus 1/3? 2/3. So the bottom was 1 minus r, and r was 1/3. So what was 1 minus 1/3? 2/3. So we'll type that in, and that will tell us what the first 12 numbers in that pattern add up to. All right, let's see. So I like to do it in steps. If you want to type it in differently, you can. Just make sure you get the same answer right. So 1 minus 1/3 raised to the 12th. So that's the top. Don't even round it. Just leave it just like that. Divide that by 2/3. And then double. Well, what are we getting pretty close to? My answer is pretty close to what? 3. It's very, very close to 3. So I'm even going to put here that the answer is about 3. And that gives you an idea. If you add up the first 12 and it's that close to the number 3, adding up the first 13 isn't going to make this much bigger. Because remember, by the time you get to the 13th term, you've taken 1/3 of 1/3 of 1/3 of 1/3 of 1/3 of 1/3 of 1/3 13 times. It's getting pretty small. So that's kind of what we're going to start to get into today. So what happens if we don't just add up the first 12 or the first 100 or the first million? What if we want to add up every single number in this sequence forever? Like every number that there is. Well, we can do it because the numbers are getting smaller and smaller and smaller each time. And eventually they don't make a difference. They're just so small they don't matter. It's when they get bigger and bigger and bigger each time, then you can't do it. They have to be getting smaller. And the formula to add up an infinite amount of numbers is actually simpler than this formula. There's less in it. This one's more complex.
So this formula is only used when you get closer to 0?
Yeah, you can only use this formula if the numbers here are getting closer and closer to 0. Here's an example where you couldn't use it. What's happening here to my numbers each time? If I did it right. Yeah, it's doubling. If the numbers are getting bigger and bigger and bigger, you can't add them all up. The answer would just get bigger and bigger and bigger and bigger. This formula only works when the numbers get smaller. Now, I guess if you said, well, just add up the first 3, well, even though they're getting bigger, I can do that. What's 5 plus 10 plus 20? 35. So I could add up the first 3. Or I could add up the first 4, even though they're getting bigger. But what I can't do is keep going forever, because they're just going to get bigger and bigger and bigger. Like, you could tell me to stop somewhere, and I can figure that out. All right, so any questions on that formula? Okay. So, all right. So this is the same section. This is part 2. So yesterday and a little bit of today, we talked about how to add up a certain amount of numbers in a sequence that stops. Even if you want to add up the first 1,000,000 numbers in a sequence, that doesn't go on forever. 1,000,000 is a lot, but it stops. We're going to look at today, how can we add up an infinite amount of numbers? How can we add up a bunch of numbers that never stop. And the only way you can do it is if the numbers get smaller and smaller, so eventually they don't make a difference. That's the only way it works. So there are actually some sets of numbers that when you add them all up forever, you get very close to an answer. You guys saw an example of that in the last problem. It was like 2.9 repeated. It doesn't matter how many more numbers you added to that answer we just had. It was just going to stay 2.9 repeated. It was not going to keep getting bigger and bigger. So the first thing we want to be able to figure out is, how can you tell if a bunch of numbers actually add up to something? Or what if they don't add up to something? How can you tell? Well, this is the notation using sigma for what we call an infinite series. What looks different about it than yesterday? First of all, there's an infinity sign on the left. When you have an n here, that means you stopped somewhere. It's unknown where you stopped, but you stopped. How about on the right side? Did anyone notice something that's different there? There's more dots at the end. So this means you have a bunch of terms at the beginning, a bunch more terms, then you get to the nth term, but then you keep going after that. So when you end something with a dot, 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 that means it continues on forever. So that's the notation for an infinite series. So adding up an infinite amount of numbers by hand, that would kind of take you a while. So we can't think about physically doing that. We can't do it, because infinite means it goes on forever. So rather than adding up an infinite amount of numbers by hand, we're going to look for a pattern. And we're going to see, what does it look like the numbers are getting close to? What are the numbers approaching? If we get an answer like 2.99999, then we know they're getting close to 3. Right? And how many did we add up in that last problem? Was it just the first 12? That last problem we did? So you could tell that it was getting close to 3 just by adding up the first 12. You could have probably figured out it was getting close to 3 by adding up the first 5. You don't have to add up that many to see what it's getting close to. All right. So this is actually kind of a review of what we just did. So here's an infinite series. And I want to get an idea of what this is going to add up to. So what I'm going to do is I'm going to add up the first 4 and see if I can tell what that's getting close to. Yeah.
Whenever you get a chance, you show that.
So we're going to add up the first 4. Then we're going to add up the first 5. Then we're going to add up the first 6. This is the formula I just showed you in the last section. Is adding up 4 things adding up an infinite amount of things? No. But it's probably a good enough idea that if I add up 4, I'm going to be able to see what this is getting close to. If you use the formula from the last section, that's your first term. That's your R. And I'm just plugging those into the formula we had. I started with a 4 as the exponent, then a 5, then a 6. So adding up the first 4, it's 2.96. What does it already look like we're getting pretty close to? 3. If you add up the first 5, you get 2.9877. And if you add up the first 6, you get 2.9959. So each term is only 1/3 as big as the one before it. So by the time you get to the 6th term, it's a third of 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 the original. It's pretty small. It's not making much of a difference anymore. Any questions on those calculations or how you would type those in?
What would be our answer that we write down?
So I'm going to show you the formula. This is just kind of getting at the idea of if you add up more and more terms, are they getting closer to something in this one? And the answer is yes. But the answer to this problem would be 3. If you could add up every term from the first one to the infinite one, it would be 3. As close to 3 as you can possibly imagine. 2.9 repeating forever.
It would be like x is less than...
Well, we would say it's approximately 3. And I'll tell you the word we use to describe it. I don't want to visualize that. Okay, I'm not worried about that. All right, let's look at this one. Now, we don't have a formula yet to add up infinitely many terms. So let's try doing like the first 3, the first 4, and then the first 5. And let's see if we notice a pattern. If we do, then that's probably the answer. If we don't, we'll talk about what that's called. Okay. What is that? The 4 is my A1. That's your first term. If you're never not sure what your first term is, you can figure it out. Plug 1 in for K. 1 minus 1 is 0. 3 to the 0 power is 1. And 1 times 4 is 4. So that's where your first term always is. And what's this? It's my R. That's what I'm multiplying by each time. Now, just think about that. I'm multiplying the previous number by 3. What's going to happen as I keep going? It's going to triple every time. So the number is going to get smaller every time? No, they're not getting smaller. This time, they're getting bigger. So let's try. So my first term times 1 minus R is 3. And we're going to add up the first 3. So that's my exponent. And in the bottom, it would be 1 minus R. All right. So what's 3 squared? Or no, I'm sorry. What's 3 cubed? 27. And 1 minus 27 is? Negative 26. You know what? I'm just going to use the calculator. It's going to be easier. So we had negative 26 divided by, what's 1 minus 3? Negative 2 times 4. So 52. So if you add up the first 3 terms in this pattern, it would add up to 52. Let's add up the first 4. It's going to be the exact same formula I had up above, except what's going to change? Make my exponent a 4. Just going to use the calculator. So 1 minus 3 to the 4th, that's negative 80. 1 minus 3 is negative 2. And then I have a times 4 in front. Oh, that's not good. So now the first 4 terms add up to 160. That's a very big jump, right? Huge jump. So I could do one more, but it's going to get even bigger. So what's happening this time is if you continue adding the terms up, the answer just keeps getting bigger and bigger. It's not going to get closer to something. And you can really tell that just by looking at this. That time it's a 3. The last problem we did, it was a 1/3. So there's a rule about that number, whether they're going to add up to something or they're not going to add up to something. So, how am I going to say this? In this problem, the sums get bigger and bigger. That means that this is divergent. Divergent means that it does not add up to something. So in this problem, the sums get bigger and bigger. This is an example of a divergent series. It's divergent. Or you could say the series is diverging. Same way. Don't worry about the top part, just the bottom part. If it's not diverging, then it's converging. Converging or diverging. Those are the only two things that can happen. So converging means adds up to a number. 2.9999999. It's getting closer and closer to something. Diverging, it's getting closer to infinity. So what we want to do is be able to figure out when is a geometric series going to converge and when is it going to diverge. Just by looking at the R. And we can tell that pretty easy. What we're doing today doesn't apply to arithmetic sequences at all. What's the rule for an arithmetic sequence? Addition. Well, if you keep adding the same thing over and over, your numbers are never going to be getting smaller. The only way that numbers can get smaller is if you multiply by a fraction. So what do you think the R value would have to be under to make the numbers get smaller each time you multiply them? It has to be under 1. Yes. If the R value is under 1, then what you're adding each time it gets smaller. What about if the R value is bigger than 1?
It's going to get bigger.
It's going to get bigger. So that's the difference between the R value. So I'm not actually going to graph this, but we're just going to look at some examples. This is the formula I gave you in the last section. And what I was going to do is just put it in the calculator and try different values of R, like 0.8, 0.9, and then something like 1.1 and 1.2. And you could do second table, and you could see the answers quickly without having to do the formula by hand. But if we typed that in, and we went to the table, and we looked at an example where R is 0.8, what do you think would happen with 0.8? Would the numbers be getting smaller and would they converge? Or would they be getting bigger and they would diverge? They were getting smaller. This would converge. What would it converge to? I don't know. I need to know what the first term in the sequence is. I don't know that. How about 0.9? Would that converge or diverge? It would converge. I mean, it's not converging quickly. If you multiply a number by 0.9 each time, it doesn't get that much smaller, but it does get smaller. How about 1.1? That's going to diverge. And how about something like 1.2? That's going to diverge because you're multiplying by a number that's going to make it bigger each time. So the key here is whether or not the R value is greater than 1 or less than 1. And actually, even if you multiplied something by like negative 0.5, that would converge too. Let's take the number 12 and multiply by negative 0.5. I get negative 6. Multiply by negative 0.5 again. I get 3. Do it again. I get negative 1.5. And that's still converging. What's happening is it's oscillating between positive and negative. But what number is it getting closer to?
Very good.
Yeah, it's getting closer and closer to 0. So from that, we didn't really do the explore on the calculator, but we just kind of did it together. If you have an R value that is between negative 1 and 1, that's what this means. So between negative 1 and positive 1. Not included, just between negative 1 and 1. Then you will converge. If you have an R value that's bigger than 1, that's going to diverge. Less than negative 1, that's going to diverge. So it's a very small R value that converges. It has to be between negative 1 and 1. Yes?
Why do people care whether or not sequences converge or diverge?
Why do they care?
Yeah, like what's the point of knowing whether or not something is convergent or divergent? Like, what does it do?
What does it do?
I
I suppose if you're looking for patterns, maybe you could tie it into cryptography somehow, like code breaking. If you can find patterns in data, just a guess.
Is that something you guys were even really curious about, like just as a group, like why this stuff matters or where it's used?
I have to find a different example that maybe it's something simpler than that, but that would be one guess.
The best one that I can think of is when it comes to like modeling functions, you need to know, like if you think about like a Taylor series or a Maclaurin series, you don't know if they converge or diverge. You don't know if your approximation is any good.
Yeah.
So if you're trying to model like an unsolvable, like a math problem you can't solve by hand, sometimes we produce these like approximations, and if you want to test whether or not your approximation is good, you're checking its convergence. So a lot of times we use stuff like this to help us approximate answers that would otherwise be unsolved.
Yeah.
That's the best use that I know.
And I told you the nice thing about something that when you're adding up infinitely many terms, the formula is a lot simpler than the finite one. Okay, so remember the finite one. A sub 1, 1 minus r to the n, over 1 minus r. Okay, that's what we had in the last section. That's what we have in this section. That's the formula for adding up an infinite amount of numbers in a geometric sequence. It only applies when r is less than 1, the absolute value of r. Could you use this when if the absolute value of r was greater than 1? You could, but the number you get doesn't really have any meaning. And what's a sub 1 again? That's your first term. And r, that's what you multiply by each time. So how about something like 0.7? If r was 0.7, would that be a convergent? Yeah. How about negative 0.8? So if I multiply by negative 0.8, take a number like 50, multiply by negative 0.8, and then times negative 0.8. Is it getting closer and closer to something? Yeah, it is going to get closer and closer to 0. It's like you're only taking 80% of the number each time. It's oscillating positive, negative, but it is getting closer and closer and closer to 0. So negative 0.8 would converge. How about 3/5? Why would that diverge? 3/5?
Oh.
What's 3/5? Like as a decimal, about right?
Huh?
What's 3/5? 0.6. So 0.6 falls within this range. So that would converge. Okay, so anything between -1 and 1. Alright, let's look at that one. So I want to look at two things. I want to look at the difference between what the terms are converging to in the sequence and what the sum is converging to. That's two different things. Sometimes people mix those up. What the terms in the sequence are getting closer to and what the sum of the terms in the sequence is getting closer to. All right. First of all, let's start with the 5. What is that? That's my first term, right? If you forget it's your first term, fill in 1 for k, and you'll get 1/2 to the 0 power is 1, and 1 times 5 is 5. So that's my first term. What's the 1/2? That's what I'm multiplying by, and what letter is that in my formula? R. That's my R. Now, how do we know in this one if we should be using the finite formula or the infinite formula? Something here tells me. Not the R. The what? The infinite sign, right? The infinity symbol. This tells you that this is an infinite summation. It's not finite. Okay, it goes on forever. So what's my term? What's my formula for adding up infinitely many terms in a geometric sequence? Great.
A1 over 1 minus R.
A1 over 1 minus R. And Jenna, what's A1? 5. Divided by 1 minus R. So 1 minus 1/2. What's 1 minus 1/2? 1/2. So what's 5 divided by 1/2? And that's not 5 divided by 2. It's 5 over 1/2. So you're trying to think about how many times 0.5 goes into 5. Yeah? 10. Yep, 10 times. So if you were to add up every number in this sequence, as far as you could go, what would it get very close to? 10. Now, let's write out the first few terms. So this is called, you call this the summation. You can also call it the limit of what all the terms add up to. Let's write out some terms. What was the first term here? 5. Now let's put the second term. Plug in 2. What's 2 minus 1? 1. What's 1/2 to the first power? 1/2. What's 5 times 1/2? 2.5. Yeah, we'll just leave it as 5/2. Have a great day, Mr. Bell. Let's do this. Was the first term, second term? Let's do the third term. 3 minus 1 gives me 2. What's 1/2 to the second power? 1/4. And what's 5 times 1/4? 5/4. What's the next term going to be? 5/8. And 5/16. Then what? 5/32. And 5/64. So now my question here is, what are the individual terms in that sequence approaching? They are approaching 0. They're getting smaller and smaller and smaller and smaller. I'm not saying it adds up to 0. I'm saying the individual terms are getting smaller and smaller, and they're getting closer to 0. So the sum of the terms is approaching 10. The terms themselves are approaching 0. Any difference? Any question on the difference between those two things? And you could check this. If you add up the first 4 of these with your calculator, you're probably going to get a number pretty close to 10. Probably going to get like 9.99 or something like that. Questions on them? All right, so that's 11.2. All right, so that's the homework for 11.2. And there's one question from last night I would like you to try as well. That's page 589. I don't see a good one. I'm just going to make one up. Let's add up the first 20 terms. All right, so here is your formula. It's going to be, so it's sum from k equals 1 to 20, and I need to make up a formula that will work. 3 times 1/2 to the n minus 1. Okay, so I've given you an r value there that will work. And I've given you the first term. So add them up. And if you're not sure, I can even write it out as a sequence for you. The first term is 3. The next term is 3/2, 3/4, 3/8. Keep going till you add up the first 20. But don't list them all out. That's not the way to do it. Okay, use the formula that I showed you at the very beginning of class. All right. And also